Let's now talk about sliding windows. So the example problem is sliding window max from lead code. So we are given an array, and we are asked to consider sliding windows of size k, which is moving from the very left array to the very right. So every time we see k numbers in the window, and we are supposed to output the maximum of the largest number in that window. So, and then we'll need to return that sequence of max values. So for example, in this example, if we look at 1, 3, -1, the max is 3. So the shifting the window by 1, we have 3, -1, -3, so the maximum is 3. Shifting again, we have -1, -3, 5, the max is 5, and so on. So we are supposed to compute this sequence of max values. So again, let's first try a brute force approach. So first, there's some taking care of the corner cases. So if k is bigger than the size of the array, then this is just not well defined. So for this question, we are supposed to return null. Otherwise, if k is 0, we are supposed to just return one element array containing 0. So otherwise, we create the array that the result, and then just for every possible sliding window, we compute their max. So we scan through the window and then get the max. So what's the time complexity? It's not hard to find. There's a loop here, which worst case n. There's a loop here, worst case k. So it's option C here. So the complexity is nk. Now, can we speed this up? We have notes here explaining this a little bit more in detail. So the worst case happens when k is n over 2. So we have around n squared over 2. It doesn't matter that much. Just worst case is quadratic. So can we speed this up? So encourage you to pause and think about it. So one idea is we don't have to find this max value by scanning through array every time. Sometimes we can know what is the max value when we shift the window, when we shift window by 1. Sometimes we don't have to scan through the whole window to determine what is the max value. So this is one way to do it. So there are two conditions that when they are true, we know that we don't have to scan through the array again. We just immediately know the max value. So the first condition is if the new value we are looking at is bigger than the max value of the previous window, then we know the new value is definitely the max of the new window. So that's pretty obvious. When that's not the case, when the value we are getting rid of, the value that slides out the window is not the same as the max, then the max doesn't change. Because we know the max value is in the window, and the value that just leave is not that. So it will be a smaller value leave. So then the max of window is the same. So that's the I call this lazy update. So I first check whether the new number is bigger than the previous max. If that's the case, then the new max will simply be the new number. Otherwise, so there's this else here. If the number that I'm getting rid of from the window, which is this num_i, is less than the max, then the max doesn't change. So otherwise, that means the new number is smaller than the old max, and the number that just get rid of it, just slide out of the window, is actually equal to the max. In that case, I will scan through the window to find the max. So even though this lazy update, normally it will improve the complexity, but there is a pathological case where the lazy update doesn't buy you much. So in fact, there is a case where the lazy update buys you nothing. So you're always scanning through the window. So I want you to pause the video and think about what case is that. What will be the worst case? Yeah, I guess should be test case. I'll fix the slide later. So the case that trigger the worst case behavior is if the array is strictly decreasing. So any new value we see will not be as big as the current max. And also, every time the value we remove from the window, it turns out to be the max. So we have to scan through the array to find it. So that is the case that we will make the lazy update not gain anything at all compared with the naive approach, except it actually performs some extra check. But we can have guaranteed better complexity than big O and K by organizing the information in the sliding window using some data structure. Because what we want in the sliding window is we want to add a value, remove a value, and then find out what is the max. Well, it turns out there are data structure that does exactly that. So it's called the priority queue. So it supports efficient add, remove, and then find either the max or the min. So in this case, we can use because the priority queue in Java, I think it's a default finding the list. So there are two ways to do it. One is we can provide when we create a priority queue, we provide these comparator, this order, which this comparator, which will reverse the order, or we can put in the negative of the value instead of putting in the actual value, and then we just, when we take it out, we put the negative again. So priority queue support these operations in login time, add, remove, and find the least element in login time. So that's the third approach here, use priority queue. So we take so we compute the max, and each time we will remove the value to be removed and add a new value, and then use the priority queue to give us the max. So actually, we learned about set and map in a previous topic. Actually, tree set will ordered set in Java. It's implemented using tree set. Will provide the same functionality. It has add, remove, and it also have first and last. So all of these are login times. So the question is, can we use tree set instead of priority queue, and what under what circumstance we can, and whether there are cases that we cannot. So what are their differences? So there are a few differences. So first, the same element can be added multiple times to priority queue. So then there will be the priority queue will maintain multiple copies of that. So when you remove one, then the other copies remains. But tree set try to implement the set interface, so each element can, the same element can only add it once. So when you try to add it again, we will not add. However, we can use a tree map to implement these functionalities for priority queue. We just map each element to the number of times it appears. So then we can also add the same element multiple times. And also tree set and tree map, they have functionality that are not supported by priority queue. For example, you can iterate over all element in the set in order. In priority queue, you cannot. The priority queue, you can only take the mean or the max. And the only way to get the next one is to delete this element. To get rid of this element, then you get the next max. So if you want to traverse the things in priority queue in order, you have to take everything out. So in the tree set, you can actually iterate through them without taking things out. So in general, ordered set provide more capability than priority queue. So in principle, they should be slower than priority queue, because priority queue implement simpler functionalities. So what it provides is kind of, in some sense, a subset of ordered set. So, but because that we can use tree set instead of priority queue in Java, or tree map. I guess we need the tree map. So then this is approach using tree map. So it's essentially replacing priority queue with tree map. So this is what we do to insert element. So we first see whether that thing exists, that number exists as a key. If it exists, yeah, then we will, this is removing that element. Yeah, so we will reduce this count by 1, otherwise we fully remove it. I guess it probably doesn't hurt to keep the element in the set with map to 0. Yeah, and we use this merge to add the element to this map. So if it doesn't exist, we will just put 1. If it exists, we'll add 1 to the current count. So we've talked about 4 approaches: the brute force, lazy update, using priority queue, and using tree map. In fact, there's a 5th approach, which is in some sense the best approach. It's actually linear time. It uses a two-ended queue, but the conceptual thing that's used there is a monotonic stack. So it uses stack, but the element has the particular properties. So the element in them are always monotonic. But it's the concept is not that easy to explain, and I view that outside the CP1. So I will not talk about how to do that here. So I want you to guess among approaches 1, 2, 3, 4. So I showed the code on the earlier slide. So which one is fastest? Well, of course, this all depends on the test case. So here I'm referring to when I submit this code to LeetCode, which one are fastest. So you can think about it and make your guess. So this is what happens when I submit to LeetCode. So it turns out that the brute force actually passed, and it's actually not that bad. So 17 milliseconds. And the lazy update is faster, so it takes 3 milliseconds. So I guess approaches that are faster than lazy update are probably the ones using the monotonic stack. And the priority queue and tree map, they are complexity-wise, they are better. Instead of nk, they are n log k. But they have they have a bigger constant factor, so we have to use this extra data structure to maintain things. Updating that actually, even though it's a log k, it's actually take quite some operation. So it turns out that they're actually slower than the brute force in LeetCode. So what does that say about these test cases? So I want you to think about that. So I think what this means is that the test case have generally relatively small value of k. So k may be in the tens. So maybe you have k maybe 10, 20. So in those cases, brute force, because it's simple, the small constant factor is actually faster than this log k. But if k is in the tens of thousands, then definitely priority queue or tree map will be will be better, faster than brute force and lazy update. Okay.